Hi, in this video, we are going to continue with our course on IOQM problem solving. This is problem number 88. I want to show you 4 or 5 different problems today. This is problem 88. Uh, at a party, every boy dances with at least one girl, but no girl dances with every boy. We have to prove that there exist two boys and two girls such that each of these two boys have danced with exactly one of these two girls. So think about what the problem statement says. Every boy dances with at least one girl, but there is no girl who has danced with all the boys. And now there are two boys and two girls. We have to show that there are two boys and two girls such that each of the two boys has danced with exactly one of these two girls. So we want a situation like this. There are two boys A and C and two girls B and D. We want to show that A and B dance together, C and D dance together, but B does not dance with C and D does not dance with A. If we can prove that this situation occurs, A and C are two boys and B and D are two girls, such that they dance like this. A and B dance together, C and D dance together, and A and D and B and C don't dance with each other. If we can show that such a situation exists, then the problem is solved, right? Okay, so what we will do here is we will assume that there is a boy A, there is a boy A who dances with B, who dances with girl B, and does, and we also know that girl B does not dance with, boy C. So right now we have assumed that there is A and B such that A and B dance together and B does not dance with C. Now, if we think about it, among the girls who have danced with C, C has danced with several girls. Among the girls who have danced with C, we want to find some girl who has not danced with A. We want to find a girl who has not danced with A. If we are able to do that, then that girl we can call our D girl, and that will finish the problem. We want to say that among the girls that dance with C, there must be some girl D who has not danced with him. And that's it. That will finish our problem, right? So how do we do this? How do we prove that there will be such a girl D, right? So what we will do here is we will assume, I will create some space here. We will choose A to be the boy who has danced with the lowest number of girls. So this is an example of a principle called the extremal principle, where in any finite set, we have a maxima or minima. So right now I'm going to choose A to be the boy who has danced with the lowest number of girls. Who has danced with the lowest number of girls. How does that help us? Let's think about it. So we know by our assumption that if a girl like D does not exist, what was special about the girl D? The girl D was a girl who has danced with C and has not danced with A. So if a girl like D does not exist, what does that mean? It means that all the girls all the girls who danced with C also danced with A. Also danced with A, right? But we have also assumed that A dances with girl B and girl B does not dance with boy C, right? So if you think about it, A dances with a girl B and B does not dance with boy C. So therefore, the number of girls that A has danced with is going to be B plus all the girls that C dances with. All the girls that C dances with. Why are we saying that? Because we have assumed that a girl like D does not exist. Girl like D was the girl who dances with C but does not dance with A, right? So since that kind of a girl does not exist, that means all the girls who dance with C also dance with A. And then B, we have already assumed is a girl who dances with A but not with C. So now we are getting that A dances with more girls than C, right? B plus all of the girls that C dances with. So we are getting A dances with more girls than C, which contradicts our assumption here, where we had chosen A to be the girl with the least number of, A to be the boy who has danced with the least number of girls. And since it contradicts the minimality assumption here, we know that then this cannot happen. Girl like D does not exist. This must be incorrect. There must be a girl like D. What is special about the girl like D? The special part is that she has danced with C but not with A. So that means that has to happen. And then we get a situation like this where we get A dancing with B, C dancing with D, and B doesn't dance with C and D doesn't dance with A. So that proves the existence of two boys and two girls where each of the boys dances with exactly one of the girls. So it is a slightly tricky problem to think about. You have to prove the existence by choosing A to be the boy with the least number of girls. And after that, you have to set it up like this and solve the problem. I hope you have understood the solution here. Let's move on to the next problem. This is question 89. And here, this is an algebra question. Prove that for any positive real number, any positive real numbers A, B, C, D, we have to prove square root of A squared plus B squared plus C squared plus D squared by 4 is greater than or equal to cube root of ABC plus BCD plus CDA plus DAB divided by 4. So a nice inequality problem here. We will use AMGM inequality to solve this one. But before we do that, we'll first prove a simpler identity. The first part is proving this lemma. A squared plus B squared plus C squared plus D squared by 4 is greater than or equal to A plus B plus C plus D by 4. So how do we prove this? What we will do is a simple simplification here. Like if this inequality is true, I can square both sides and try to take the difference of this. I'm squaring both sides and taking the difference of these quantities. And I'm going to check the sign of this expression, right? So this will be 1 by 16 here and A plus B plus C plus D whole square. So I will take 1 by 16 out common. And what we have here is 4 times A squared plus B squared plus C squared plus D squared minus A plus B plus C plus D whole square. And that becomes equal to 1 by 16 outside. And you have basically 3 times A squared plus B squared plus C squared plus D squared. And you have a minus 2AB minus 2bc and so on. There are 6 terms here. 2 times ab plus ac plus ad plus bc plus bd plus cd. This is what I'm getting, right? Now, this expression, we want to confirm whether this expression is positive or negative. Okay. So how do I do that? What you can do easily here is write this as a sum of multiple perfect squares. So if you think about it, this is equal to 1 by 16 a minus b whole square. If you take 1a square, 1b square and 2ab plus a minus c whole square plus a minus d whole square plus b minus c whole square plus b minus d whole square plus c minus d whole square. Check it out. Here a square appears 3 times, b square appears here, here, and here. Similarly, c square appears here, here, and here, and d square also appears 3 times. So you get 3 times of this term, and all the minus 2ab, 2ac, 2ad, 2bc, 2bd, and 2cd terms are accommodated. So basically what I have shown is that this quantity is positive because this is a sum of squares. So this is greater than equal to 0, which means that this quantity is greater than equal to 0, which means our inequality here is true. So right now I need to prove this step, this inequality, but so far what I have done is proven this lemma, right? And the proof is by simple squaring and bringing everything to one side and showing that the quantity that you get is the sum of squares and therefore it is positive, right? So let's work on the next screen now. We have lemma 1, which says root over a square plus b square plus c square plus d square divided by 4 is greater than equal to a plus b plus c plus d by 4. And what we have to show root over a square plus b square plus c square plus d square by 4 is greater than equal to cube root of abc plus bcd plus cda plus dab whole divided by 4. That is what we need to show. So what I will do now is I will work on this RHS part here. And let's think about it. ABC plus BCD plus CDA plus DAB by 4. That is the same thing as if I group the terms together, take half outside, I get ABC plus ABD, ABC plus ABD by 2 plus BCD plus CDA by 2. That is the same thing. And now I'll write it like this. Half of, here I will take AB common and it is C plus D by 2. And here I will take CD common and that is A plus B by 2. So far I have not done anything. I've just grouped things together. And now what I will use is ANGM inequality, which says A plus B by 2 is greater than equal to root AB. So what I know is A plus B by 2 is greater than equal to, this square is greater than equal to AB. So AB is less than equal to A plus B by 2 whole square, right? So that is what I will be using in this next step. So I will say this is less than equal to half. Instead of AB, I will write A plus B by 2 whole square times C plus D by 2. And instead of CD, I will write C plus D by 2 whole square times A plus B by 2. So this is an inequality, and obviously I can take what common here? I can take A plus B by 2 times C plus D by 2 common, right? So the next step I'm writing above here. So this is equal to, this inequality is equal to A plus B by 2 common, C plus D by 2 also common, and you get inside, you take the half inside, you get a plus b by 4 plus c plus d by 4. So basically, you get equal to a plus b by 2, c plus d by 2, and inside a plus b plus c plus d by 4. This is what I'm getting so far, right? So notice what I started off with. I'm getting RHS is less than equal to this. I started with the RHS expression, but without the cube root here, right? So I will write it on the next screen. This is what I started with. ABC plus BCD plus CDA plus DAB by 4. And I have shown so far that this is less than equal to A plus B by 2, C plus D by 2, A plus B plus C plus D divided by 4. This is what I have shown so far, right? And if you remember the lemma that we had, we will be using that again. But before that, I will use the fact that AB is less than equal to A plus B by 2 whole square again. How do I use it? I'll use it on these two terms. Okay. So this is my x and y. So product of x and y will be less than equal to x plus y by 2 whole square. So I can say this is less than equal to a plus b by 2 plus c plus d by 2 by 2 whole square, right? And I have a plus b plus c plus d by 4 here, right? Now this thing is equal to, if you see here, it is a plus b plus c plus d by 4 whole square. So multiply it with this, you'll get a plus b plus c plus d by 4 whole cube, right? So what I'm getting is this expression here. And I have already proved in lemma 1, if you recall, I had shown that root over a square plus b square plus c square plus d square by 4 is greater than equal to a plus b plus c plus d by 4, right? So this quantity is less than equal to cube of this, right? If you cube it, I will get this, right? So basically what I'm getting is square root of a square plus b square plus c square plus d square by 4 whole cube, right? And I'm getting here, this quantity is less than equal to this, right? So how do I simplify this? What I can do is take power 1 by 3 on this side. What we get is cube root of ABC plus BCD plus CDA plus DAB divided by 4. If I take cube root on both sides is less than equal to, I'm getting here square root of a square plus b square plus c square plus d square divided by 4. And that is what we needed to prove. This is what we needed to show. So remember what we have done here. We proved this lemma by simple squaring and rearranging pure algebra. Then we looked at the RHS of the desired inequality and applied this AMGM principle several times, but only after regrouping the terms intelligently. First, I grouped ABC, ABD together, BCD, CDA together, took AB common and CD common in both, applied the AMGM inequality on AB and CD. Then I grouped out or took common a plus b by 2, c plus d by 2 outside, and I got an a plus b plus c plus d by 4. And then I applied AMGM once again on the first two factors. And then the problem is solved after that. Right? So hopefully you've understood this problem. We'll move on to the next question now. This is question number 89. I think it is problem 89. Let me just verify once. Or maybe problem 90. Okay, so it is problem 90 now. Okay, let's look at this problem. We have to determine all integers a, b, and c such that a square plus b square plus c square plus 3 is less than ab plus 3b plus 2c. So we have discussed problems like this before. There are three variables and one inequality. It's not likely that you will get a value for A, B, and C unless you do something really clever. And we have seen problems like this before. Usually, it is a powerful condition like sum of squares or something. So if I can express the whole thing as sum of squares, three perfect squares, then probably I will be able to say something. So what I will do is bring everything to one side, a square plus b square plus c square plus 3 minus ab minus 3b minus 2c is less than 0. Now, what we will do is try to group these terms intelligently in order to make perfect squares. So one thing I can notice is c square minus 2c. So I can immediately write plus c square minus 2c plus 1 and minus 1, right? And I have a square ab, right? And b square and 3b. So how do I handle b square and 3b? What I have to do is I have to use this AB term. So I can do a square minus 2 times a into b by 2 plus b square by 4. So this will handle this term, AB term, a square term, and b square by 4. So what do I have left with now? I have 3b square by 4 left over. I have minus 3b and I have a plus 2, right? Plus 2 because 3 minus 1. So I will remove this minus 1 from here, right? Okay. And then we have to think of what we can do here. So c square minus 2c plus 1 plus 2. Okay, right. Okay. So I feel like I'm missing this part is not becoming a clear perfect square. So let me just think. Uh, okay. Right now, I need an extra 3 here. If there was a plus 3 here, it would be nice. Right now, I have a plus 2, which doesn't work, right? So let's think about the initial problem for a moment. We had LHS is less than RHS, right? And both sides are integers. Both sides are integers. LHS is less than RHS. So then instead of having a plus 3, what I can say is LHS plus 1 will be less than or equal to RHS, right? If both sides are integers and can take only integer values and LHS was lesser than RHS, then this inequality is correct. LHS plus 1 could be still less than RHS or it could be equal to RHS, right? Because the next integer after LHS would be LHS plus 1 and it could be equal to RHS or could be still smaller than RHS. So what I will do here is not work with the initial problem, I will change the problem a little bit and I will add plus 1. 1 plus this, and then my inequality becomes a non-strict inequality. It is not less than 0, it is less than equal to 0. And now there I have a plus 1 here and I have a less than equal to 0 here, right? And now it is much better because I can say 3b square by 4 minus 3b plus 3, and I will take 3 common. B square by 4 minus b plus 1, and this can be written as 3 times b by 2 minus 1 whole square, right? B by 2 minus 1 whole square is a perfect square here, right? And now I can write the whole thing here, LHS, as a minus b by 2 whole square plus c minus 1 whole square plus 3 times b by 2 minus 1 whole square less than equal to 0. Notice that if you work with the original problem, it was a less than inequality, and that would not help you bring the perfect square here. I needed to convert it from LHS less than RHS to LHS plus 1 less than equal to RHS. And now this is done because sum of 3 squares cannot be less than equal to 0 unless each of these is equal to 0 on its own. And therefore you have A is equal to B by 2, C is equal to 1, and B by 2 is equal to 1. So basically A is equal to 1, B is equal to 2, and C is equal to 1. These are the only integer values which satisfy this inequality. And you can check it out. If you put 1, 2, and 1 for ABC, you are getting this. And if you take any other integer values, it won't work. So that is the solution. It is a tricky problem because if you directly work with this inequality, you have a less than inequality which doesn't work out. But if you add a plus 1, since both sides are integers, you can write this and then it works out, right? Okay, let's move on to the next problem. This is question 91. The question says, among 8 points on a circle, not on a circle, on or inside a circle, on or inside a circle, prove that there exist two whose distance is less than the radius of the circle. Here the distance means the distance between the 2 points. Distance between those 2 points. This is a very nice problem. It's a little tricky, but it uses pigeonhole principle. So think about it. There are 8 points on or inside a circle. The points could be anywhere on the circle's perimeter or inside the circle also, right? So if there are 8 points on or inside a circle, like we know for sure that only one of them could be the center of the circle. Only one of them could be the circle center, could be the circle's center. So what that means is there is greater than or equal to 7 points. 7 points that are not the circle center, that are not on the circle center. So 7 or more, 7 or 8 points are lying on the circle and they are not on the center, right? So technically, let's imagine 7 points, A1, A2, A3, A4, A5. I'm drawing them randomly, A6 and A7. Let's imagine 7 points on or inside the circle. And this is the eighth point which was on the center, right? So what you can think here is if you join the central point to all of these, right? You will determine basically 7 radiuses. Obviously, you have to extend the segment sometimes because some points might be interior, right? What I mean to say is, if you draw a line segment from the point that is on the center to any of these, right? You will determine 7 radii, correct? At least 7 radiuses. A0 to A6, A6 is inside the circle, so you'll have to extend it to make it a full radius, right? Now, in case one of the points was not on the center circle, then A0 is also another point here. Then you will take center as the point and join all of them. And then there will be 8 radii, right? So what we have, we'll right now work with the case that there are 7 radii that are determined by the point from the center and joining the segments between A0, A1, A0, A2, and so on, right? And since there are 7 radii and the sum of all the angles is 360, the sum of all the angles around here is 360 degrees. We know that at least one of the angles between is less than 60 degrees. At least one of the angles between the radii, at least one of the angles between 2 radii is less than 60 degrees. Why? Because the circle can be divided into 6 sectors of 60 degree at the center, and there are 7 points. So one of the points lies inside one of the sectors, right? So what we are saying is there will be 2 points, for example, A6 and A7. Here the angle would be less than 60 degrees, right? So now you have to think of these 2 points. It is possible that A6 was here and A7 was here and the center was here. What we know right now is that there exists at least one such pair where this angle is less than 60 degrees. This is A0, correct? Now think about it. What we will do is join this, join A6 to A7, A0 to A7, and A0 to A6. So we have a triangle here. We know this angle is less than 60 degrees. So we are guaranteed that angle A7, A0, A6, which is less than 60 degrees, is strictly less than one other angle of the triangle. What do I mean by this? What I mean to say is, since this angle is less than 60 degrees, it cannot be the maximum angle of this triangle, right? It is definitely not going to be the maximum angle, because if this was the maximum angle, then the other angles are smaller than 60 and the overall sum of the angles of the triangle will never be 180. So since this angle of this triangle is less than 60, there is some other angle, for example, this angle, which is bigger than 60, which is bigger than this angle, right? So we are saying alpha here and beta here. We know that alpha is bigger than beta. And there is guaranteed to be one angle in the triangle which is bigger than beta, right? So we know that this implies that the side A0, A7 is bigger than A6, A7, right? Basically, what we know is that A6, A7, this side, the side opposite to our angle, is going to be smaller, right, than A0, A7, or going to be smaller than the other side. We know from triangles that bigger angle subtends bigger side opposite to it, right? So since our angle here is lesser than one other angle of the triangle, the side opposite to it is also going to be lesser than one other side of the triangle, right? So what I know is that there is definitely A6, A7, the side opposite to our angle is less than either A0, A7 or A0, A6. And what is the maximum length of this? The maximum length of A0, A7 or A0, A6 can be radius of the circle, right? Because A0 was the center and A0, A7, the maximum value will be the radius of the circle. So what we have is there must be a side A6, A7, which is less than the radius of the circle in length, right? So what we have found basically are 2 points A6 and A7 whose distance between them, which is A6, A7, is less than the radius of the circle. Think about what steps we did. We had 8 points. We said that at least one point will be only 1 point can be the center. So at least 7 or more points will be distributed on or inside the circle everywhere. And since there are 7 points, and you can divide the circle into 6 sectors of 60 degree, 2 of these points lie in the same sector. So that means the angle between A0, A6 and A0, A7 will be less than 60 degree. Then you make a triangle A0, A6, A7. And then you say that since one angle is less than 60 degree, that means there is other angle, at least one other angle which is bigger than 60, which means at least one side will be larger than A0, A6, A7. And since one side is larger, at least one side is larger than A6, A7, that means the maximum distance between A6, A7 can be the radius of the circle, right? So that concludes our problem. Basically, we have proved that the maximum distance between two of the points making the line segment is at most the radius of the circle. Okay, so that finishes off this question. I have some more problems, but what I will do is I will stop at this point for this particular video, and we will continue with problem 92 in the next session. Question 92 onwards will be in tomorrow's session. I will try to make these IOQM problem videos regularly from now again, and hopefully you will learn from these problems that I will be solving. So I'll see you tomorrow in the next class, and that's it for now.